So this video is the second part of the first one that you saw on carbonyl condensation reactions. It takes up from where we left in that lecture video. In what would be the first part of this video, we started looking at carbonyl condensation reactions. So let me just remind you, we covered aldol condensation reactions. Then we considered whether aldols could be done with two different molecules, and that, of course, is what we called mixed, or sometimes you'll see this referred to as crossed aldol condensations. We cover that. Then we also consider the case of whether an aldol reaction could be done in order to make a ring, and indeed we can, and those would be your intramolecular aldol condensations. And after that, we consider the idea of whether you can carry out an aldol on something other than an aldehyde and a ketone. What about using esters? And so we looked at aldols using esters, except that there we don't call the reaction an aldol anymore, remember, but we call that a Claisen condensation. Then, of course, we consider, just as in the case of an aldol, can you do a mixed or crossed Claisen? And you saw that indeed we could do that, being judicious with our choice of reagents. And remember, in the case of a mixed Claisen, both of your molecules don't have to be esters. As long as one of them is an ester, the other one could be an aldehyde or a ketone. That would still fall under the class mixed Claisen reactions. And so that is where we had left off the last time. So the next thing we want to cover, to follow the same pattern as with aldols, can you actually do intramolecular Claisen reactions? And the answer is you can, except that we no longer call it these reactions Claisen. We call this type of reaction Dieckmann cyclizations. So let's go over a Dieckmann cyclization, which again is nothing more than an intramolecular Claisen reaction. So imagine if you have a molecule such as this one, in which I have an ester on this side and I have an ester on that side, right? So if I were to treat this, let's say, with a nice strong base like sodium ethoxide in ethanol as the solvent, and then once the reaction is done, you need a proton source, so let's just say a nice solution of a dilute acid, then we can actually end up getting a ring. So what happens here? Well, your base is going to deprotonate at the position alpha to the carbonyl, and whether I do it here or here, you realize it's exactly the same thing. So I will start counting from here, 1, 2, 3, 4, and 5. And that tells you what's the size of the ring that you're going to form here. So carbon number 1 will take the electrons and attack carbon number 5. The pi electrons move up to the oxygen and they quickly reform the carbonyl. Why? Again, because you have a built-in leaving group there. So the ring that you've made is 1, 2, 3, 4, and 5. So let me draw the 5-membered ring. So now carbon number 1 is attached to carbon number 5. So I'll just call this one, just randomly, arbitrarily, carbon number 1, which has now formed a bond with number 5. So this is 2, this is 3, this is 4, and 4, of course, is attached to carbon number 5. So what do you have on carbon number 5? Well, you reformed your carbonyl. And on carbon number 1, you have the ester attached to it. So here you have an ester. So that would be the product of a Dieckmann cyclization. Now, if you really look at this molecule, it should actually look quite familiar, because if you focus on the following. So let me just redraw this for 1 second in a way that you've probably seen before should look more familiar. So there's my carbonyl. Beside that, I have this ester, so I'll go ahead and put the ester. So this should remind you, of course, if I go ahead and I cover that, that should remind you of acetoacetic ester. So it means I can now do reactions on this just like we did when we were looking at the acetoacetic ester synthesis. Well, for example, this alpha position, which is in between the two carbonyls, is quite acidic, and I could attach an alkyl group here and then subject that to some acid and heat and carry out a decarboxylation reaction. And we have the lecture video that goes along with that. Now, if I wanted to form a 6-membered ring instead of a 5-membered ring, then I would just have to extend this chain by 1 to accommodate that size ring. So that is it really for a Dieckmann cyclization. All right, so what else? Well, someone smart considered the following. You will recall when we were doing the chemistry of aldehydes and ketones, we brought up the issue of 1,2 versus 1,4 addition. Well, someone smart by the name of Michael, and hence we call this the Michael addition reaction. Consider the following, all right? What if we have something like acetoacetic ester, and we were to deprotonate that? So let's say sodium ethoxide, 1 equivalent, because if you recall, having 2 equivalents changes where you're going to deprotonate. So that would deprotonate the expected alpha position between the 2 carbonyls. Now, what if I now throw in not a regular aldehyde or ketone or ester, but I use an alpha-beta conjugated system like that? What happens here is that this is going to attack this carbon, so it's a 1,4 attack. These pi electrons move over to form a carbon-to-carbon double bond, and these pi electrons move up on your oxygen. So this reaction is going to be done sodium ethoxide, and you're going to use ethanol as your solvent. So what is the product that you get from that? Well, if we follow the movement here, here is the carbon that attacked, which is this one. It's now attached to that carbon. And I'll number the one that is attacked just so that you can follow, numbering strictly for purposes of following the movement, not how you would actually number this for nomenclature purposes. 1, 2, 3, and 4. So the attacking carbon, which is this one is attached to number 1. 1 is attached to 2. 2 is attached to 3, but there's now a double bond. 3 still has 4, and at number 3, you have your O minus. So this is the intermediate that you're going to form from that 1,4 attack. Again, this is a 1,4 attack, not the usual 1,2 attack where you would attack the carbonyl carbon, which is what we've been seeing up to now in all of the aldols, Claisens, and Dieckmann cyclizations. So then what's going to happen next is that you are going to protonate. So you reform the carbonyl, the electrons move over to carbon number 2, and carbon number 2 is going to reach over, and it's going to pick up a proton from the ethanol. It's going to pick up a proton from the ethanol that you're using as your solvent. So carbon number 2 reaches over and picks up a proton, kick those electrons in. So the product that you will end up getting from this is going to be the following. That's still attached to 1. 1 is attached to 2. 2 is attached to 3. 3 is attached to 4. There's a reforming of the carbonyl at 3, and carbon number 2 picked up that proton. And there is the product of your Michael addition. Let me do another one. So let's say that this time I use, well, let's just use, let's just say I take this ketone, and what I do is I deprotonate it with sodium ethoxide in ethanol. That would therefore give me, of course, this. I'm showing it this way. I could show the enolate version, which is what we normally do. In fact, let me do it just to remind you that, of course, this can have its enolate version, which is that. If I now throw in my alpha beta unsaturated molecule, so let's say this time I use an alpha beta unsaturated aldehyde, and again, for purposes of keeping tabs, I'll call this 1, 2, and 3. So carbon number 3 is the carbonyl. Carbon number 1 is your beta carbon. That's the one that's going to be attacked in a 1,4 fashion. So reform your carbonyl. This alpha carbon, alpha in the cyclohexanone, reaches over and attacks carbon number 1. Pi electrons move over to form a double bond between 2 and 3. And the pi electrons here move up to your oxygen. So what do you end up getting as your product here? Well, the attacking carbon, which is this, is now attached to 1, which is attached to 2, which is attached to 3, but there's a double bond between 2 and 3. There is still the hydrogen there, and of course you have an O-, so that's going to be your intermediate. And then, of course, what will happen is you have your ethanol, which is providing your proton source. You reform the carbonyl at number 3. The electrons move to number 2, and then number 2 reaches over and grabs a proton from your solvent. So the product that you're going to get here is therefore going to be, right, 1, 2, 3, 1, 2, 3. You reform the aldehyde at carbon number 3, and that is a Michael addition. Now, in these, in a Michael reaction, the species that is deprotonated and attacks is what is called a Michael donor, and the molecule that is attacked, which is your alpha beta unsaturated molecule, is what is called a Michael acceptor. So those are two terms you should be familiar with or remember. The Michael donor is the attacking species. The Michael acceptor is the one that is attacked in a Michael addition reaction. Next reaction is the Stork reaction. So this one is Stork reaction. Now there's more than one reaction that's named after Gilbert Stork, so you have to be careful that you recognize which one it is that we're doing here. So here's what Gilbert Stork recognized. So we're doing the following. We are forming enolates, and then enolates are, of course, attacking what in general would be an electrophile. So we can get alpha halogenation, alpha alkylation. We can get these aldol condensations, Clasons, and Diekmans, and even the Michael addition just now. What he recognized is, okay, if I look at that enolate, let's compare it then with the following species which we have actually seen before. If we look at that, remember this is what is called an enamine. So where did we get enamines? We get enamines whenever an aldehyde or a ketone is reacted with a secondary amine. There's a lecture video for that, and you can go back and look at it. That's the video on a pair of videos that's covered aldehydes and ketones. And if you look at the second one of those two videos, you will see where we go over formation of enamines when an aldehyde or a ketone is reacted with a secondary amine. And what Stork asked himself is, well, couldn't we do the same thing? Couldn't these electrons on the nitrogen come down, the equivalent of reforming your carbonyl, and then the alpha carbon here can reach over and attack an electrophile? And so what he did is he essentially is carrying out what is a Michael addition, except he's using an enamine as opposed to an enolate. So here's how this happens. So let me just start from the very beginning to remind you, and you can look at that video to remind yourself of the mechanism. If I were to take that cyclohexanone, that ketone, and I actually treated it with this secondary amine, what you will end up, there's an acid catalyst, of course, involved in carrying this out. What you will end up forming is the following enamine, where I now have nitrogen like that, right? So I've made the enamine. And what Stork said is, okay, what if I know? So the first part, I'm just reminding you, the Stork reaction begins here once we've made it, and we should know how to make the enamine. So what Stork said is, okay, what if I have this alpha beta unsaturated ketone? Again, to keep tabs 1, 2, 3, and 4, the nitrogen moves its electrons over to form an imine. That means the electrons move to this carbon, and this one takes them and attacks 1. The pi electrons move to form a double bond between 2 and 3, and these pi electrons move up to your oxygen. So what is the product that you get from that? Well, the product looks like this. I now have double bond to the nitrogen, and there is a plus charge. The attacking carbon here is now attached to number 1, which is attached to number 2, which has a double bond with number 3, which still has number 4, and of course there's an O minus there. All right, and then what happens? Well, instead of using ethanol in these Stork reactions, what we do is we just throw in a little bit of water for a reason I'm about to explain. So if I throw in water for the proton source, you reform the ketone at carbon number 3, and carbon number 2 takes these electrons, the pi electrons, and is protonated. But it turns out this is like the hydrolysis of an imine, and what I'm going to get when I hydrolyze the imine is I'm going to get the carbonyl here, the original molecule. So here is the product that I get. Under those conditions, the imine is hydrolyzed and I get that. And the rest of the molecule is going to be 1, 2, 3, and 4. And there is your product of a Stork reaction, which I'll remind you is really nothing more than a Michael addition, but instead of using an enolate, we're using an enamine. That's it, really. Let me do one quick one here. So let us say that you have, so I'll just start at the enamine. Suppose I actually have, in fact, let me start at the ketone. If I take that ketone and I actually treat it with, this time let me just use the following, NH, secondary amine, acid catalyst, then you know that what you're going to get from that is going to be an enamine that looks like this, right? All right, beginning there is where the Stork comes in. What if I now add to this, let's say an alpha beta unsaturated aldehyde like this, 1, 2, and 3. 1, 4 attack occurs. The nitrogen moves its electrons down to form the imine. This alpha carbon reaches over and attacks number 1. The pi electrons move over to form a double bond between 2 and 3. And the pi electrons move up to place a minus charge on the oxygen. So the product that I actually get from this now has the nitrogen with, of course, a plus charge in the imine form. The attacking carbon here is attached to 1, which is attached to 2, which has a double bond to 3, and 3 has an H and an O minus. And then, of course, we're going to throw in our H2O, which does double duty, right? You reform the carbonyl at carbon number 3. carbon number 2 reaches over and it's protonated, and at the same time, you end up cleaving the imine and placing back your oxygen. So what you end up getting is imine is gone, and I now have the original oxygen. And then I have 1, 2, and 3. So 1, 2, and 3. And there is the product of the Stork reaction, right? Which, one final time, is nothing more than a Michael addition using an enamine as opposed to an enolate. So one last reaction we need to cover under these carbonyl condensation reactions, and this one is called a Robinson annulation reaction. Now this is probably the most complex one because it involves two reactions. So essentially what Robinson did is he didn't invent new chemistry, but he coupled two reactions together and of course named them the new process after himself. A Robinson annulation is nothing more than a Michael addition reaction followed by an aldol condensation. And so it can get a little bit complex and confusing, but hopefully you can follow here in what I'm about to do and look at the patterns that I'm about to highlight. So let's say that I start off with the following molecule that should look familiar, acetoacetic ester. And I'm going to react this with this alpha beta unsaturated ketone. So I take and I treat this with sodium ethoxide. So this, to remind you, is where the Michael addition reaction is going to occur. So the base is going to deprotonate at the preferred alpha position, the one between the two carbonyls, as opposed to this alpha position. You will reach over and do your 1,4 attack. This moves over and those move over. So the product that you're going to get from this is therefore going to be the following. So here's the carbon that attacks. It attacks this one. So notice I have 1, 2, 3, 4 carbons. 1, 2, 3, 4. And I'll just put numbers here just this time to keep tabs. The attacking carbon, the alpha 1 here is attached to 1. So that's 1, that's 2, that's 3, and that is 4. There's now a double bond between 2 and 3. And you have the O- at carbon number 3. Right, so this is what I'm going to form. Now, what will happen here, of course, is the enolate prefers to be in keto form, so it will simply do the keto-enol tautomerization, or if you prefer to think of it as, well, you're going to get the typical protonation here. And so what you will end up getting is going to be the following. One, 2, 3, 4. The carbonyl is at number 3. All right, so there's the product of the Michael addition part of the Robinson annulation. What happens if I throw in sodium ethoxide again, a nice base? Well, this is where the aldol is going to actually occur. Now, if you look at this molecule, you realize that you have several alpha positions that you could, in theory, deprotonate. This carbon is alpha to that carbonyl, acidic. That carbon is alpha to that carbonyl, and it's acidic. That carbon is in between two carbonyls. We would normally say, well, that's where it's going to deprotonate. And then we have that carbon, which is next, or alpha to that carbonyl, 4 positions. Now, remember, right, let me just remind you that what I have here is the Michael donor, the one that's deprotonated and attacks. And what I have here is the Michael acceptor. So notice the pattern. This part of the molecule, the product, here, this is what came from the Michael acceptor. And that part of the molecule is what came from the Michael donor. So this part comes from the Michael donor. This part comes from the Michael acceptor. So the deprotonation in the aldol step is invariably going to happen right where you had the part that corresponds to what originally was your Michael acceptor. So it's either going to be here or here. Now, how do you decide which of those it's going to be? Well, if I deprotonate here, it will either attack this or that. So let's count. 1, 2, 3, 4. It would form a 4-membered ring if it attacks here, or 1, 2, 3, 4. It would form a 4-membered ring if this is the deprotonated site and you attack here. 4-membered ring if you attack there. If I deprotonate here and I attack the ester, 1, 2, 3, 4, 5, 6, which is a much more stable ring. If it attacks a ketone, 1, 2, 3, 4, 5, 6, which again is a more stable. So again, where am I going to deprotonate? Clearly there, because by deprotonating here, whether I attack the ester or the ketone, I end up getting a 6-membered ring. So let me review that very, very quickly. This part of the molecule is what originally was part of the Michael donor. This part of the molecule is what used to correspond to the Michael acceptor. In the second step, when I throw in the base, where am I going to deprotonate? I'm going to deprotonate an alpha to a carbonyl that corresponds to the part that used to belong to your Michael acceptor. How do I then determine whether it's that alpha carbon or that alpha carbon that gets deprotonated? Usually you can do it very simply by looking at the size of the ring that you will make. If I deprotonate here and it attacks the ester carbonyl, 1, 2, 3, 4. If I deprotonate here and it attacks the ketone carbonyl, 1, 2, 3, 4. If I deprotonate that position and it attacks the ester, 1, 2, 3, 4, 5, 6, much more stable ring. If I deprotonate here and it attacks a ketone, 1, 2, 3, 4, 5, 6. In this particular example, this will reach over and attack the ketone and not the ester. So again, I will form a 1, 2, 3, 4, 5, 6-membered ring. Now, I will now put numbers here strictly for purposes of following what has happened so that you don't lose track, not because this is how you would actually number this for nomenclature. So I'll say 1, 2, 3, 4, 5, and 6. So 1 is attacking 6, so I'll go ahead and draw my 6-membered ring. So again, 1 is attacking 6, so I will just arbitrarily say that is 1 and that is 6. So beginning at 1, I'll work my way around till I get to 6, right? 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, and then 5 is attached to 6. 1, 2, 3, 4, 5, 6, which is 1, 2, 3, 4, 5, 6. All right, once I've made that ring, what else do I have? Well, on carbon number 6, I will have a methyl group and an O minus. So a methyl group and an O minus, which we know is going to be protonated to an alcohol. So let's just do that now instead of taking time to draw something else. Carbon number 2 has a carbonyl. So therefore, I have a carbonyl there at number 2. And carbon number 5 here has the ester. So carbon number 5 has an ester, and that is what I get from the aldol addition. But we know that that's not the final product because, of course, under the conditions in which you do this, you will get the dehydration to give you the aldol condensation, and the double bond will be between 6 and 1. I lose the OH plus a neighboring proton from carbon number 1. Why is that the case? Well, look at your product. When you draw the product, what you see is if I place the double bond there, then the double bond is in conjugation with your ketone, right? And so that's normally how things are going to happen. So again, simple, not simple, I shouldn't say simple. But let me just zoom a little bit out so you can see this in its entirety. Okay, so let me just review. You have your Michael donor. Your base deprotonates. The Michael donor then attacks the Michael acceptor. Move these electrons over, move them out. You get this as your first intermediate, and that, of course, undergoes its rearrangement or protonation. You get this. So this part of the molecule, clearly originally came from the Michael donor. This part of the molecule originally came from your Michael acceptor. So once I've done the Michael addition, out of all the possible alpha positions next to carbonyls that I can deprotonate, first of all, deprotonation occurs at what used to be the Michael acceptor, and you prefer to deprotonate here because by deprotonating here, whether you attack the carbonyl of the ester or the ketone, you will form 6-membered rings. Because if you deprotonate it here, whether you attack the ester or the ketone, you would form 4-membered ring. So once carbon number 1 attacks carbon number 6, you have your 6-membered ring formed. I arbitrarily designated that as 1 and that as 6. So working my way around 2, 3, 4, 5, 6, 2, 3, 4, 5, 6. Then just fill in with what you know you have. Carbon number 2 has a carbonyl, so I put in my carbonyl there. Carbon number 5 has an ester, so I put the ester there. And carbon number 6 has a methyl and the O-, which ends up as the alcohol. And so your final step is the condensation step, and you're going to form your double bond at that position in conjugation with ketone. And we will work examples of this reaction in class, a couple more, and I'll give you some practice sheets to work on it. So one final thing that I do want to mention, which is related to what we're doing here, and this, let me just zoom in a little bit. Okay, so this falls under what you will normally see in textbooks. Some textbooks will cover this, others won't. Alkylation of alpha and beta positions. So if you recall, when we were actually looking at chemistry of aldehydes and ketones, if I want to add an alkyl group in a 1,4 sense, I have to use a Gilman reagent because a Grignard gives me a 1,2 attack. And so what I will end up getting here is that, and I'll show you in 2 steps here. So the way the reaction proceeds is that I will get an attack here. These electrons move up here. So in other words, it looks something like this. You can think of the reaction like that. So that what you end up having is you have the R of your Gilman there, and you have an O-. And then typically what happens is you reform here, and you have to have a proton source, which is normally just water in the second step. And so this is how you end up getting your final product, which is the 1,4 addition of a Gilman on an alpha-beta unsaturated carbonyl. So now consider this part here, right? So consider the following. So if I'm at this stage, the middle part, the enolate part, so here I have the enolate and I've attached the R with the Grignard. What if instead of just throwing in water and protonating that alpha position, what if I actually added a nice alkyl halide that I'm just generically calling R prime X? When I reform the carbonyl, the alpha carbon reaches over, attacks, and you kick that out. And so what I end up making here is carbonyl. Here's the R that I had originally attached, and here is an R prime. So what I've actually done, notice, is I have actually alkylated both the alpha and the beta positions, and by starting off not with a regular ketone, but with an alpha-beta unsaturated ketone. And an actual example of this, let me just show you one that was published, was the following. They started off with the alpha-beta unsaturated ketone. They first treated this with diethyl copper lithium. There is your Grignard, which means, of course, that you would attach the ethyl here. And then in this step, they added methyl iodide. And so the product that you end up getting from this is the ethyl group is at the beta position, the methyl group is at the alpha position. And you see where you can actually control this reaction as to what you put in the alpha, what you put in the beta, and you do this reaction in one single quick step. And that's it for the chemistry of these molecules when they undergo alpha condensation type reactions.